Alright, I have the new stream up. Oh, I just realized that this chat isn't going to work. Because that's the old chat. So I have to close this chat. Actually, I'm just going to minimize it for now. I have to pop out this chat. And then I'm going to do this, which should just be blank. Oops, I got to make it a different size. Sorry, normally I do all of this before we start, but okay. I do not know what the heck happened there. Like, I've been using this program for 3 years to stream, and then today it's just like, you know what? We're gonna break 3 times in a row. Excellent, just what I wanted. All right. Anyway, we managed to get through those problems. I'm gonna let people filter in. And as they do, you can hit rewind to watch the video. If it loads in and your video is blurry, what you can do... Oh, goodness, I'm going to have to try this again and see if this works. What you can do is, when you click on your video, there's a button right here that says Settings. Set the quality to 1080p60. I have no idea if that's showing up on the... Yeah, you can see what I'm doing there. So, set the quality to a different video quality. 1080p60 is the best one. And it will make it not blurry. You can see mine in the background is blurry, but it's a preview window. I don't give a shit what mine looks like. I'm looking at it on my screen here. So that is something that you can do. All right, let's keep going. So, oh, again, there's the homework practice. I don't know if that was up there before. I believe it was because I had to go back a few pages. All right, let's do the last bit of Chapter 3, and then we'll start Chapter 4. The last little bit of Chapter 3 defines metals versus nonmetals. This is going to be very, very relevant for the next 2 chapters. Chapter 4, we're going to deal with pretty much all metals, and then Chapter 5, we're going to deal with pretty much all nonmetals. We're going to explore the chemistry of those 2 substances independently. We're going to define a metal as some sort of substance that has the following properties. And it has to have all of these properties. And those properties are high thermal and electric conductivity. What that means is that you can heat them easily, and you can conduct electricity through them easily as well. Not necessarily at the same time, but... So, for instance, a cast iron skillet is a metal because when you put it on the burner, it heats up very quickly. It doesn't resist heating. If you were to, like, hook it up to, like, some sort of circuit, I don't know why you would do this, you could conduct electricity through it as well because it's made of iron. The other thing that metals are they have properties called malleability and ductility. What that means, something that's malleable means that if you hit it with a hammer, it doesn't shatter into a million pieces. Instead, it tends to retain its composition in terms of, like, all of the pieces stay stuck together because they're held together through metallic bonds, but the shape deforms. In other words, if you hit something, it will become a thinner and thinner and thinner sheet the more you hit it. Something is ductile if you can pull it along a dimension, and it gets longer and longer and longer, but thinner as it goes. In other words, if you want to make copper wire, you just take a piece of copper and you just pull it, and you pull it, and you pull it some more. And eventually, it will be a wire of the gauge that you desire for whatever application you're doing. For example, telephone wire has a different gauge of copper than, say, copper wire used to tie something to something else. Why would you do that? I don't know, but we had it in the lab, and that's what I used. The last property of metal is that it's shiny. So metals have high luster. This is a property from electrons being very mobile across the surface of a metal. When light interacts with this, the result is that you get a reflection. that is very similar to what you'd see in a mirror, depending on the metal that you use. And we call that luster. Bender is made of metal because he constantly says, "Bite my shiny metal ass," so there you go. That's the proof. That's all the proof that you need. Now, a nonmetal has none of these properties. All of these things are false. For example, iodine shown here. If you hit iodine with a hammer, it will crumple into, or it will crumble into a bunch of tiny little pieces, right? You can do this with charcoal too. If you drop charcoal on the ground, it'll just break and splinter and fragment, right? It also doesn't hold heat super well. You can catch it on fire because it has chemical energy, but its temperature doesn't increase very easily. You have to really hold a torch to it. It also doesn't conduct electricity. If you try and conduct a wire through it, it won't work. And as you can see here, iodine is certainly not shiny. So nonmetals have no properties of metals. Well, what about the things that sort of have properties of metals and like maybe they're shiny or conduct electricity well, but they don't do the other things? Well, those are called metalloids. Metalloids have some of the properties of metals, but not all of the properties of metals. So here I've shown silicon. Silicon is great because we can use it for computing. But why do we use it for computing and making computer chips and stuff out of that? Well, we do that because it conducts electricity, but not super well. It slows the electrons down that pass through it such that we can control their movement through logic gates. And thus we can use silicon as a basis to create a circuit board. That's kind of the extent of my knowledge on it. I'm not a materials scientist. So. All right. I think, yeah, here's my picture of the periodic table. All the elements that touch the staircase right here, and this staircase is shown on P table. What color do I have selected? Let's get black here. All of the elements that touch the staircase with one or two exceptions. So this is called the metal, non-metal staircase. And P table should have the staircase on there. Oh, it doesn't. Look at that. Okay. It just has everything color-coded. So everything that touches the staircase is a metalloid. Everything on the left is a metal. And everything on the right is a non-metal. And then the metalloids touch the staircase, with two exceptions. One is aluminum and the other is polonium. And the way that I remember that is the dog food Alpo. This right here, astatine is super radioactive. It's not really worth worrying about. Also, I can't do the Alpo mnemonic with at in there. At Alpo. I don't know. So yeah, there are not that many metalloids that have some of the properties of metals. Most elements fall into one category or another. Everything down at the bottom in those bottom two rows are all metals because they effectively go in this gap right here. So they're all metals. Alright, that's chapter 3. And we're going to skip all the rest of the stuff on electron configuration. So I'm just going to do this. Look at all the things that we're missing. Yay! And then, hooray. We get our little... Oh, we don't get anything. Because my music doesn't work, because everything is ruined today. That's okay. There's supposed to be like a woohoo, but I think this slide just might not have that in there, so whatever. Alright, give me just a second. I'll get the chapter 4 slides going. And alright. Chapter 4 has a little bit of an introduction of something that is going to be useful for you in this class. It says here that you need to memorize these. Hey, it's an online class. Guess what you don't have to do? Just look it up when you need it. But you'll want to have these handy, and you will eventually want to learn these. So these are what are called the polyatomic ions. Polyatomic ions are common ions that we're going to see in not just this class, but in biochemistry and biology and other locations too, but primarily those. So if you're taking Bio 211 at some point, which I think virtually everybody who's taking Chem 121 is, you're going to need to know the polyatomic ions. Because when I say, oh, I want to have a phosphate buffer, or oh, I want to react with a nitrate, or something like that, it's going to be assumed that you know what that means. Because they're so common and they're everywhere. Now, depending on your textbook and which edition you got, so if you got the version from the bookstore, you're probably going to have the list I'm going to show you on the next page. If you got an earlier edition, there were more ions in there, and any other edition might have the wrong ions. So what I'm going to have you do is, using this list right here, these are the polyatomic ions that I want you to know what they are. And when I say what they are, I mean you need to know the name of the ion. So for example, nitrate. That's not what I meant to do. Now you need to know the name. So for example, nitrate, and also its formula, NO3-. The formula is both the elements and their numbers and the charge on the top. So that minus symbol is important. That is not something that you can ignore. So those are on this slide. You're going to want to have that handy. Those will come up at some point later, and we will discuss them at that point. Okay. But for now, just make sure that you have this list available whenever we need it. All right, so we only have about 10 minutes left, but what we can do is we can actually get through probably valence electrons. The first section that we're going to talk about in Chapter 4, which is all about ionic compounds. In the first section here, we're going to talk about the forces that hold things together, and so these are called bonds. So far, in Chapter 3, we've introduced atoms. And so we said, what is an atom? Well, it's a collection of protons and neutrons and electrons. Now what we're going to do is we're going to start to explore, how do atoms interact with other atoms? And the answer is right here. They interact through what's called a chemical bond. A bond holds two or more atoms together. We're going to look at two types of bonding here. The first one's ionic bonding, and we're going to spend this whole chapter studying that. Covalent bonding is Chapter 5. We're going to get to that one later on. Oops. So we're going to start with ionic bonding. Ionic bonding, at its simplest premise, is simply this. I have an ion that's positively charged. I have an ion that's negatively charged. They attract to each other. So if I have two oppositely charged ions, they will attract because opposite charges attract to each other. Now, how the heck do I do that? How do I make an ion to begin with? We started in Chapter 3 by saying atoms have the same number of protons and electrons, right? If I were to change the number of protons and electrons so that they were not the same, I would get an ion. Now, specifically speaking here, the thing that we are changing is the number of electrons, because it's very difficult to change the number of protons. They're in the nucleus, they're stuck to a bunch of neutrons and other protons. Can't really do that effectively. But electrons buzz around the outside, and they're very easy to remove. So I could go bink and just like flick one off, right? Or add an extra one in there. In either case, the number of electrons will be different than the number of protons, and therefore we have formed an ion. If I add electrons, I get a negatively charged thing, and if I remove electrons, I get a positively charged thing. So if I can do one of each to two different things, something I add an electron to and something I take away an electron from, those two things now have opposite charges, and they attract to each other. The attraction that forms is what we call the ionic bond. And if you form ionic bonds, the substance that you are looking at that does that is an ionic compound. So I just have some examples here of fool's gold, which is an ionic compound, and also table salt, NaCl. Now you'll notice that with my diagram here, I can't really zoom this in and draw it, but you can see when I zoom in that I have a bunch of sodium plus ions and a bunch of chlorine minus ions. And they sort of alternate, right? Plus, minus, plus, minus, plus, minus, right? So if I were to draw that over here, here's my plus, here's a minus. What ends up happening is that the ionic bond between my ions goes in any direction that it wants to. So the attraction is in all directions, up, down, left, right, side to side, front and back, diagonal, however it wants to go. And so you end up forming this repeating array of things that are attracted to each other. So if I put something in this space, it'd have to be this, right? Because it would be attracted to its neighbors, the minuses. And something that would go over here would be that. And then this. And then this. And so I make all these ionic bonds, which I'm now drawing as solid lines, and I shouldn't be. But that's okay. So when you make an ionic compound, you just get a series of repeating ions over and over and over and over and over. Now, some physical properties of ionic compounds is that they make crystals. The reason for this is because things tend to coalesce together in shapes that form cubes. This is just sort of a phenomenon that occurs, and it has to do with the fact that you can be in contact with more things if you are on a plane as opposed to sitting on top of it. For example, if I had... I'm just going to draw the charges here. If I had something like this, and I made, like, say, another layer of it like that, and I had a hole here, and I said, where will plus go? Well, if I put it right here, I'm only attracted to one thing. But if I put it in here, I'm attracted to three. So filling in holes and making a flat surface is more desirable. And stuff only really gets packed on the edges when it has to. So if you see a crystal and it looks like it's got these kind of like cube shapes in it or rectangular prism type things in here, it looks very like blocky and geometric. That's a good sign that what you're looking at is an ionic compound. Other things ionic compounds do is when you dissolve them in solution or you melt them, they conduct electricity. And high melting point. We already talked about that. Okay, cool. And then finally, again, there's our picture of what an ionic bond is. So that's the first type of bond that we're going to talk about. We're going to talk about that in Chapter 4. So your job is to understand what this illustration means. Positive thing, negative thing, attracted together. Cool, we can do that. The second type of bond that forms is called the covalent bond. Covalent bonds do not form from ions. They form from neutral atoms. So again, make sure that we aren't mixing up the names here. We're going to discuss the form of the covalent bond in more detail in Chapter 5. But suffice it to say that compounds that are covalent behave very, very differently than compounds that are ionic. So their bonding must be very unique, relatively speaking. And we actually observe that in many different ways. Their melting points are very low. Many covalent compounds are liquid at room temperature or even gaseous. So, for example, oxygen, O2, that you're breathing, is a covalent compound. It's a gas at room temperature. Water is a liquid at room temperature. It is also a covalent compound. And covalent compounds do not conduct electricity pretty much in any state. Water is a non-conductive substance. That might seem very strange to you if you have heard, like, oh, you don't want to be in the water when lightning strikes. And the reason that we say water is a non-conductor is because it is better at conducting electricity than air is, but it's not as good as, say, a metal. For instance, if I were to have my choices of stand out in the open on, like, dirt, be in water, or stand on, like, a metal surface, I don't know, like a really just wide open metal surface in a lightning storm, I would not want to pick the metal. That would be awful. Do not do that. All right. We're going to talk about, again, covalent bonds in Chapter 5. So don't worry about this just yet. We only have 3 minutes, so I'm not going to start this. When we come back tomorrow, what we're going to do is we're going to talk about valence symbols, which are a special way of drawing, or I'm sorry, Lewis symbols. I don't know why I said valence symbols. We're going to talk about Lewis symbols, which are a special way of drawing pictures. And those pictures are going to help us throughout the quarter to understand how bonds form and how various substances interact and behave. So, I do want to thank everybody for coming out to the lecture. I apologize for all of the weirdness with the stream going down all of a sudden. Like, it looks like not everybody came back, and that's real unfortunate. Hopefully people will see that there is a second video that has the rest of this. Hopefully there will not be any more technical difficulties, because I hate them. We finished Chapter 3, so there will be a quiz for Chapter 3 that is going online. I will get to that later today. But for now, make sure that you get quiz number 2 done. It is due on Wednesday. We'll talk a little bit about lab number 2 tomorrow. Heads up, I may need to use Wednesday as an extra day for an extra lecture, just so that we get through all the material before the midterm, because the midterm is chapters 1 through 5. We'll definitely get through Chapter 4. I gotta make sure that I have enough time to get through Chapter 5, though. Okay, so yeah, I think that's it for me. Have a wonderful weekend. Or not weekend, I'm sorry. Have a wonderful Monday. We'll see you tomorrow.